Every story about scientific revolution wants to give you a lightning bolt, a genius standing under a tree, an apple falling, a shout of eureka in a bathtub. But the story I want to tell you today isn't about a flash of insight. It's about a number. A small, ugly, inconvenient number. 8 arc minutes. That's it. That's the whole revolution. 8 arc minutes of angle in the sky, smaller than the width of your fingernail held at arm's length, and it was enough to shatter 2,000 years of certainty about the shape of the universe. Today I want to show you why trusting that tiny number instead of throwing it away is maybe the single bravest act in the history of physics, and why the way it broke the old cosmos is still quietly the operating principle behind everything we do in science now. Now look, to understand why 8 arc minutes could break a universe, you have to understand just how sacred the circle was. For 2,000 years, from Aristotle through Ptolemy, all the way up through Copernicus, everybody agreed on one non-negotiable rule. The heavens are perfect, and perfection means circles. Not ellipses, not ovals, not anything lumpy or asymmetric. Circles, uniform, unchanging, eternal circles, moving at constant speed. This wasn't a scientific conclusion. Let's be very precise here, and it was a metaphysical assumption dressed up as physics. The Earth down here is corrupt and changeable. Things rot, fall, break. But up there, past the moon, everything was supposed to be different, untouchable, geometrically pure. Even Copernicus, the great revolutionary who ripped the Earth out of the center of the universe and threw it in orbit around the sun, didn't touch the circles. He kept them. He just moved the center. The circle was too sacred, even for the man who broke geocentrism. So when a young, half-blind, deeply religious mathematician named Kepler inherited the most precise set of planetary observations the world had ever produced, decades of naked-eye measurements of the planet Mars, painstakingly recorded by an astronomer named Tycho Brahe, everybody, including Kepler himself, fully expected those observations to confirm a circular orbit. That was the job. Take the data, fit it to a circle, maybe add an epicycle or two to clean up the small stuff, publish, done. This is how astronomy had worked for 2 millennia. But it gets even more interesting when you consider what Tycho's data actually was. This is the part people skip over, and it's the part that matters most. Tycho didn't have a telescope. Nobody did yet. What he had was obsession. He built enormous brass instruments, quadrants and sextants, the size of small buildings, and for over 20 years he tracked Mars across the sky with a precision nobody thought was possible with the naked eye, accurate to about 1 or 2 arc minutes. To put that in perspective, that's roughly the angular size of a coin viewed from half a kilometer away. Before Tycho, astronomical measurements were sloppy enough that a 5 or 10 arc-minute discrepancy between theory and observation was just noise. You'd shrug, adjust an epicycle, move on. Tycho's data changed the rules of the game because now the noise floor was so low that a real discrepancy had nowhere to hide. Let me sketch this for a second. Imagine the orbit of Mars as this loop I'm drawing here, and imagine the predicted position from the best circular model of the day as this point, and the actual observed position from Tycho's measurements sitting just here, 8 arc minutes away. 8 arc minutes doesn't sound like anything. It's a rounding error. It's the kind of gap you could paper over with an extra epicycle, tilt a wheel a little, adjust an eccentric, and nobody watching from the outside would ever know the difference. And that's exactly what Kepler could have done. He had every professional incentive to do it. He had spent years, trying to fit circular and near-circular models to Mars's orbit, and he'd gotten unbelievably close. Close enough that any of his predecessors would have called it a triumph and gone home. Now, don't get confused by the popular version of this story, the one where Kepler just discovers the ellipse in a flash. That's not what happened. What happened is stranger and, honestly, more instructive. Kepler got a model that matched Tycho's data almost perfectly. off by only those 8 stubborn arc minutes, and he made a decision that, in the context of his time, was almost unthinkable. He said the discrepancy is small, but Tycho's data is too good to be wrong by this much. If my circle is off by 8 arc minutes, the problem isn't the data. The problem is the circle. The point is actually quite subtle, and it's worth sitting with, because it's the exact same logic that separates good science from bad science today. Anyone can fit a model to data if you're willing to fudge the residuals, wave away the outliers, tell yourself the error bars must be bigger than they look. What Kepler refused to do was rescale his confidence in the data to protect his confidence in the theory. He inverted the priority. The measurement became more trustworthy than the metaphysics. That sounds obvious now. It was radical then. For 2,000 years, theory told you what the data should look like, and any deviation was assumed to be measurement error because the theory, perfect circles, perfect heavens, was assumed to be metaphysically guaranteed. Kepler flipped it. The data doesn't answer to the theory answers to the data, full stop. Now let's follow that logic to the chalkboard, because once you make that flip, you can't unmake it, and the consequences cascade fast. If the circle is wrong, what shape is Mars's orbit actually tracing? Kepler spent years. This part of the story is genuinely brutal, page after page of what he himself called his war on Mars, testing egg shapes, ovals, every geometric figure he could construct by hand, with nothing but logarithms he was inventing as he went, and calculations that took months to check by hand. And eventually he landed on it, an ellipse. Not a circle with the sun conveniently at the center, but an ellipse with the sun sitting off to one side at one of the 2 focal points. Picture that loop I sketched a minute ago. Now stretch it just slightly and move the sun away from the middle to one of these 2 points inside it. That small, almost imperceptible stretching is the entire correction. That's what an 8 arc-minute error looked like, once you found the right shape to absorb it. But here's where it gets even more depressing for anyone attached to the old cosmic hierarchy, because the ellipse wasn't even the worst part. The worst part was what came with it. If planets move on ellipses instead of circles, then they're constantly changing their distance from the sun, closer here, farther there. And if you track their actual speed, they're moving faster when they're close and slower when they're far. That's Kepler's second law, the equal areas law. A planet sweeps out equal areas of its orbit in equal times, which mathematically forces it to speed up near the sun and slow down away from it. And this was, in its own quiet way, more heretical than the ellipse itself, because uniform, constant speed motion wasn't just a convenient assumption about the heavens, it was tied to the very definition of celestial perfection. Constant speed was supposed to be a signature of the unchanging, eternal nature of the heavens, as opposed to the messy, variable, speeding up and slowing down world down here on corrupt, changeable Earth. Kepler's data said the planets don't care about that distinction. They speed up, they slow down. The heavens, it turned out, behave exactly like everything else in nature, governed by relationships not decorated by perfection. Now, I want to be very precise about what actually broke here, because it's not just an astronomy fact, it's a whole world view. For 2,000 years, the universe had been understood as fundamentally divided: perfect, circular, unchanging heavens above, imperfect, irregular, changeable earth below. 2 different sets of physical laws for 2 different realms. What Kepler's stubborn insistence on trusting 8 arc minutes of data actually did was erase that boundary. If planetary motion isn't uniform and circular, if it's shaped by something that produces ellipses and varying speeds, then whatever is happening up there has to be governed by the same kind of quantitative causal relationships that govern things down here. It's a bit of a nuisance for anyone who liked their cosmos tidy and hierarchical, but the ledger must balance, and once it does, there's no more up there and down here. There's just one universe running on one set of rules, and those rules can be found by looking hard enough at the numbers. And this is exactly the crack that Newton climbed through half a century later. Because once you accept that planets move on ellipses, and once you accept that their speed changes in this very specific, mathematically constrained way described by Kepler's laws, you're left with an obvious, screaming question. Why? What is actually doing that to them? Circles moving at constant speed don't obviously need an explanation. The ancients treated that as just the natural default behavior of perfect celestial matter. But an ellipse with a planet speeding up and slowing down in a precise, predictable pattern, depending on its distance from the sun, that looks like the signature of a force that gets stronger as you get closer, weaker as you get farther. Kepler's three laws, extracted stubbornly from Tycho's data, became the exact numerical fingerprint that let Newton reverse-engineer the inverse square law of gravity. Kepler didn't know he was measuring gravity. He thought he was doing something closer to sacred geometry, honestly. He had his own mystical ideas about the harmony of the spheres that turned out to be wrong. But the data didn't care what he believed about why it looked the way it did. It just sat there, stubbornly ellipse-shaped, waiting for someone else to explain the mechanism. Now, let's follow that same logic just a little further, because I think this is where the story stops being about the 17th century and starts being about how physics still works today. Every major shift in our understanding of nature, everyone, has followed roughly the same shape as Kepler's war on Mars. You have a beautiful, well-established theory. You have new data, more precise than anything that came before. And you find a small, nagging residual, a discrepancy the size of 8 arc minutes, or its modern equivalents. The precession of Mercury's orbit off from Newtonian prediction by a stubborn 43 arc-seconds per century that nobody could explain until Einstein's general relativity accounted for it exactly. The faint wobble in galaxy rotation, curves that shouldn't be there, according to the visible matter alone, which either means there's dark matter we can't see, or our theory of gravity itself needs another Kepler-style correction. Small numbers, inconvenient numbers, numbers that are easy to dismiss as error, and devastating when you don't. Now, don't get confused and think the lesson here is always trust every anomaly and throw out every theory that doesn't perfectly fit. That's not it either, so that way lies chasing noise forever. The actual discipline, the thing Kepler modeled for everyone who came after him, is knowing the difference between noise and signal, and having the nerve to act on that judgment even when the signal is small and the theory you're threatening is ancient, beautiful, and universally believed. That's a genuinely hard skill. It requires respecting your data enough to know when it's better than your assumptions. Tycho's 20 years of obsessive measurement gave Kepler a noise floor low enough to see the 8 arc minutes clearly. Without that quality of data, the anomaly would have been invisible, buried in sloppy measurement, and the circles might have survived another century. So here's where I want to leave you, because I don't think this is really a story about the 17th century, or even really a story about astronomy. It's a story about what happens when you refuse to protect a beautiful idea from an ugly fact. Kepler had every reason to fudge the number. He was religious, he believed deeply, almost mystically, in cosmic harmony, in the idea that God had built the heavens according to elegant geometric principles, and circles fit that belief far better than lopsided ellipses ever would. Trusting the 8 arc minutes cost him the model he wanted to be true. It's easy to underestimate how much nerve that takes, because we already know how the story ends. We already know ellipses are correct, so it feels inevitable in hindsight. It wasn't inevitable. It was a choice made against the weight of 2,000 years of consensus and against his own personal belief in what the universe should look like. And that, to me, is the real ending of this story. Not, here's how we learned planets move in ellipses, But here's the moment humanity discovered that the universe doesn't owe us elegance on our terms. It doesn't arrange itself according to what we find beautiful or symmetrical or theologically satisfying. It just is what it is, and it will tell you exactly what it is in stubborn little residuals of 8 arc minutes or 43 arc seconds or a wobble in a rotation curve, if you're precise enough to measure it and honest enough not to explain it away. Every real breakthrough since has followed the same quiet, unglamorous discipline. Build an instrument good enough to see the gap, then have the nerve to trust what it shows you, even when it means giving up the shape of the universe you were sure you already understood.